welcome back to our final talk. So the final speaker is our very own Ender Lamaison, telling us some exciting result of his about uniform Turán density. Okay.
Okay, thank you. So yes, this is a problem about in hypergraph Turán. So the natural point to start is with the definition of the Turán density of a hypergraph. Fortunately, you have already seen this slide 4.5 hours ago on the very first slide of this conference. But in case someone was not there, so basically the Turán density of a hypergraph is the largest value of D such that you have arbitrarily large hypergraphs with edge density arbitrarily close to D, which do not contain F as a subgraph. And the whole point of this slide is that for graphs, this is very easy. It's the Erdős theorem. It depends only on the chromatic number. But determining the Turán density of hypergraphs is very hard, even for 3 uniform hypergraphs. Cases as simple as K4 or even K4 minus an edge, they turn out to be really hard. And for example, this is the conjectured asymptotically extremal configuration for K4. And it has edge density 5/9. But the remarkable thing about it is that, well, you notice that it has its vertex set split into 3 equal parts. And each of these 3 parts does not contain any edge. So we have 3 independent sets of size linear, and in fact, n/3. So even though globally, this hypergraph has edge density 5/9, it's very dense, there are very large parts of it which are completely empty. So this motivated Erdős and Sós to ask what happens if you do not allow something like this. If you require not just that you have a very high density somewhere in the graph, but actually everywhere in the graph. So this stronger notion of density is what we call uniform density. So we are going to say that a hypergraph is d epsilon uniform dense, and we denote this uniform with this symbol with 3 dots, if every linear size subset, every set of size at least epsilon n vertices, has density at least d minus epsilon. And we are going to let it to 0, so every linear sized subset of the vertices has edge density very close to d. So how does the Turán density problem look like if we replace the weaker notion of just edge density with the stronger notion of uniform density? So what we now have is that we want to find the large, for a fixed hypergraph F, we want to find the largest value of D such that we have a sequence of hypergraphs which are arbitrarily large, which have uniform density tending to D, and which do not contain F as a subgraph. So again, the difference between the 2 notions is that we have replaced just having edge density D in the whole graph with actually having density D on every linear sized subset of our graph. And the purpose is, again, to avoid constructions like the one that I showed before, but also, for example, if you remember about the Erdős theorem, for graphs in the classical Turán density, the extremal construction is a complete multipartite graph. And that also has linear sized independent sets. So we will not allow something like that. So what do we know about the uniform Turán density? Well, for graphs, it is known for every graph, and in fact, it's always 0. It's true that if every linear sized subset of your vertices has positive density, then you do contain arbitrarily large cliques. It's an easy consequence of the regularity lemma. However, the same is not true for hypergraphs, even for 3 uniform hypergraphs. And I am in this talk, I am going to talk, everything that I mention after this point is going to be about 3 uniform hypergraphs. Now, there are several constructions that show this fact. There are several constructions of hypergraphs which have positive uniform density. So every part of the graph is dense and yet do not contain arbitrarily large cliques. There's in fact a very nice one I believe it was by Erdős and Rödl, based on random tournaments. But the one that I want to talk about today is related to something called palettes. And this is a construction that was introduced by Rödl in the 80s. So a palette consists of 2 things. It has some set of colors. In this case, I chose 3 colors. And it has some, and the set of colors is finite. And it also contains some list of ordered triples of colors, which we call the admissible triples. And we use these palettes to generate uniformly dense hypergraphs with the following procedure. Let's say that we want to construct a uniformly dense graph on n vertices. In this case, let's say 7 vertices. So what we do is take the vertices from 1 to n. And here it's important that they come with a certain ordering, in this case from left to right. And then for every pair of vertices, we pick one color from our list uniformly at random. And then for every triple of vertices, we need to decide whether we place an edge there or not. And the rule is the following. For every triple of vertices, we look at the 2 smallest colors and the color that they span, the smallest and the largest color and vertices and the color they span, and the 2 largest vertices and the color they span. That gives us an ordered triple of colors. In this case, for the vertices 1, 2, and 6, that would give us the ordered list of colors red, blue, and green. And then the rule is that if that ordered triple of colors is an admissible triple, we place an edge there, otherwise we do not. So for example, here, if we have the vertices 2, 3, and 6, you can see that the edge 2, 3 is blue, the edge 2, 6 is green, the edge 3, 6 is red, or those pairs are blue, green, and red. And the triple blue, green, red is not an admissible triple, not in that order. Therefore, we do not place an edge there. And the result is going to be some hypergraph. Using standard probability tools, you can see that, the expected value of the edge density is going to be the number of admissible triples divided by the number of colors cubed, in this case, 4/27, for example. And using standard concentration arguments, you can show that with high probability, the result is going to be uniformly dense with this density. And that means that if we can find, if we have some hypergraph F that does not appear as a substructure here, as a subgraph, then its uniform density is going to be at least the density of the palette. So let's give a way of an explicit way of describing this situation. We are going to say that a 3-graph F admits the palette P if there exists an ordering of the vertices of F and a coloring of the pair of F in such a way that every edge of F induces an ordered triple of colors that lies precisely on the list of. Now you can see that if F appears as a subgraph of the construction that I did above, it is going to certainly admit the palette P just by taking the same vertex order as here, left to right, and the same coloring of the pairs of vertices as we have on the picture on the left. So therefore, if F does not admit the palette P, then the density of P acts as a lower bound on the uniform density of F. Okay, I mentioned that there are other constructions, even some nicer ones. So why am I focusing on palettes? Why are they so important? Well, it turns out that for all the exact results that are known about uniform Turán density, the sharp lower bound constructions come from palettes. So for example, Rödl, and Schacht characterized which hypergraphs have uniform Turán density 0, and it is precisely in terms of palettes, on whether they admit the palette with just 3 colors and 1 triple. There was also the question of computing the uniform Turán density of K4 minus an edge, and it was shown to be 1/4, and again, the lower bound comes from a palette. And I wrote here 2 sets of authors. The first set of authors proved it using the flag algebra method, whereas the second set of authors later gave a proof using the hypergraph regularity method, which is the same method that every consecutive result about uniform Turán density followed. Later, there was the question of computing the uniform Turán density of tight cycles, in the case when they are not tripartite, because otherwise it's 0. And once again, the lower bound comes from a palette. And then together with Garbe and Kral, we constructed a hypergraph which has uniform Turán density 1/27, and that's significant because 1/27 is the density of this palette on top, which has just 3 colors and 1 triple. So this is the palette that acts as the lower bound of our construction. And it's not just the exact results that have been found. Also, for all the other hypergraphs that have been looked at, the best known lower bound comes from a palette. So therefore, it makes sense to ask, if we fix some hypergraph F, what is the best lower bound that you can prove just by giving palettes that F does not admit? Well, we can describe this optimal lower bound as the palette Turán density of F. Now, seeing that for all examples that we know so far, the best lower bound come from palettes, the natural question to ask is it always going to be sharp? Are all the lower bounds that you can prove on uniform Turán density coming from palettes? So this was a question that had it appears on a survey by Ryer, and that's the first time that it appeared in a paper, but it had circulated in the community for a while before that. And indeed, the main theorem of my talk is that yes, this is the case. The palette Turán density is the same as the uniform Turán density for all 3 graphs. Okay, that's a nice result, but what is the point of this result? Why is this interesting? So the Erdős stone theorem was very important because it related to the Turán density of graphs, which was at the time not so well understood, with the chromatic number that was much better understood. In this case, however, we are relating the uniform Turán density to a parameter that is worse understood than the uniform Turán density. So what are we gaining in exchange? Well, it turns out that computing the palette Turán density of a hypergraph seems, at least from all the examples that we know so far, seems much easier than computing the uniform Turán density. And perhaps one big example of this is the case of the cycles. So I told you that in 2021, a set of fibers determined that for all non-tripartite cycles of length at least 5, the uniform Turán density is 4/27. Well, that proof took 30 pages, and it's a very technical and complex proof. Whereas 3 years earlier, Jacob Cooper had shown in his master's thesis that the palette Turán density of the cycle is 4/27. And it's just a 5-page proof, and there's really not too much complicated in that proof. So it would be great to have had a black box that allows you to just take the proof for the palette Turán density and tell you, oh, it's also going to work for the uniform Turán density. Let me show you another result. So I don't have time to go through the details, but I told you that Rödl and Schacht characterized which hypergraphs have uniform Turán density 0, and it came in terms of this palette. Well, now the entire proof fits in one slide, because essentially you just take the same vertex ordering as in if F admits this palette, you take the same vertex ordering, you take the same coloring of the pairs of vertices, and it is going to work for any non-empty palette that you take. And in this case, it's cheating a bit, what I'm doing here, saying, oh, it fits in one slide, because of course, all the crux of the proof, all the important parts of the proof are being shoved into my main theorem. So it's not really making it easier, it's just sweeping it under the rug. And I would agree. However, in the next case, I would agree that I am not doing this, that the crux of the proof is still in the slides. Again, I do not have much time to go through it, but for the case of K4 minus an edge, you can prove that the uniform Turán density is 1/4 in 2 slides. These 2 slides, you just construct some auxiliary graph on any palette that does not admit K4 minus an edge, and end up getting some Cauchy-Schwarz, or actually just AMGM inequality, and see that the density of that palette must be at most 1/4. And in this case, I would argue that yes, the most important parts of the proof are still on those slides. Like this computation right here is the important part of the proof, and everything else is just like everything else in the proof by Rödl and Schacht is technicalities that you need in order to reduce everything to this single equation. So this really does make things a lot easier. And I want to mention that it is not just reproving old stuff that we have been doing. We have also proved some new results on the uniform Turán density. So for example, if we take the K star, so the K star is a hypergraph on K plus 1 vertices, where we take one vertex to be the center. Here I drew it on top. And then you take all edges that contain the center and 2 other vertices. And that's the K star. Now, Rödl and Schacht had looked at the uniform Turán density of stars, and they had given both a lower bound and an upper bound. And together with Zhuo Wu, we showed that for large enough stars, the lower bound is sharp. So again, now we have new results on uniform Turán density, and this, and in fact, we have now infinite families of values of the uniform Turán density. So I'm now going to say a few things about the proof of the main theorem. And so how do we prove this? So let's recap. We already know that the palette Turán density of a hypergraph is certainly a lower bound on the uniform Turán density, and we need to show the upper bound. That's the hard part. So let's denote the uniform Turán density of F by pi. Our goal is for every epsilon to find some palette P with density at least pi minus epsilon that F does not admit. So what do we know about the value pi? Because it is the uniform Turán density of F, we know that there exists a sequence of F-free hypergraphs which has uniform density pi. So then the goal would be to find P essentially as a subgraph, within this sequence of hypergraphs. Now this has the drawback that it is not well defined what does it mean for a palette to be a substructure of a hypergraph. So for the moment, let's take the definition that a sequence of hypergraphs contains a palette P if every hypergraph which admits P is a subgraph of some element of our sequence. This certainly would be enough to prove our main theorem. However, once I go a bit more in depth into my proof, you will see that I mean this containment in a stronger way. So if we want to prove the main theorem from scratch, the sequence of steps would be like this. You start with the sequence, with this sequence of hypergraphs. You apply the hypergraph regularity lemma to get a regularity partition. Now, Ryer showed that you can perform some cleanup of this on this hypergraph using the fact that the sequence of hypergraphs is uniformly dense, so that all linear-sized subsets have the same edge density. And you obtain something that is called a reduced hypergraph. And then my contribution here, what I do in the paper, is the final step, which is taking this reduced hypergraph and finding a palette inside of it. So I'm not going to say much about the hypergraph regularity. Again, the only important part that is remarkable about it is that usually in the hypergraph regularity partition, you get multiple layers. In the case of 3 uniform hypergraphs, you get 2 layers. But because you know that the hypergraph is uniformly dense, you know that all vertex sets have the same edge density, and that allows you to get rid of that bottom layer. So let's go straight to my starting point, to where these reduced hypergraphs that Ryer introduced. So what is a reduced hypergraph? An n-reduced hypergraph is a hypergraph whose vertex set is partitioned not into n parts, but into n choose 2 vertex sets. Each of these vertex sets has two subindices between 1 and n. And the property of this hypergraph is that each edge, so this is a 3 uniform hypergraph, and the 3 vertices in each edge are in 3 parts of the form Vij, Vik, and Vjk. So for example, here you can see that the blue edge has 1 vertex in V13, 1 vertex in V18, and 1 vertex in V38. So for every triple of indices ijk, we denote the tripartite hypergraph induced by these 3 parts, the constituent ijk. And then we say that an n-reduced hypergraph has density at least d if all the constituents have edge density at least d. And there is one special family of reduced hypergraphs that are important for the proof, which is the blow-up of palettes. So given some palette, we can construct an m-reduced hypergraph by taking m choose 2 copies of the set of colors. These are our vertex sets. And then every constituent is going to consist of all the triples of all the ordered triples of colors, which correspond to the admissible triples in the palette. Okay, so essentially this is a palette, a reduced hypergraph in which all the constituents look exactly the same. So our goal is to show that if this n is large enough, then every n-reduced hypergraph with density at least p contains an envelope of a palette of density at least pi minus epsilon. So with a small drop in the density, we can find a blow-up of palette. And this is the stronger containment relation that I mentioned at the beginning. Okay, and how do we find such a such a blow-up of palette? Well, we can assume without loss of generality, and in fact, it is going to be the result if you come from a regularity partition. We can assume that all the vertex sets in our reduced hypergraphs have the same size, which we denote as L. So within each of the vertex sets, we are going to label all the vertices from 1 up to L. And then within each constituent, every edge now gets encoded as a triple of integers from 1 to L. So what we get is that each constituent is some subset of the triples of integers between 1 and L. So now let's look at 3 scenarios. The ideal case, the best scenario, is if all the constituents encode into the very same set. In that case, we are done because then the reduced hypergraph itself is a blow-up of a palette. There's nothing that we have to do. The good case is if, okay, not all of them are different, but what happens is that as n tends to infinity, the size of the vertex sets remains fixed. Well, in that case, there's only finitely many, a bounded number of possibilities that each constituent can be. So by Ramsey's theorem, we can find a large subcollection of indices such that every triple of indices induces the exact same constituent, and that reduces us back to the ideal case. So this case would still, if we can reduce to the good case, we are still done. And then we need to look at the general case. And in the general case, what we need to do if the number of vertices just tends to infinity, well, our goal is to select within some of the small subsets of vertices in such a way that all triples of vertices induce density at and doing that, we will have if this does not tend to infinity as n tends to infinity, or so if this only depends on epsilon, then we will have reduced ourselves to the good case, and we will be done. Unfortunately, such a vertex selection cannot be done just randomly. Like naive random choice does not work. The Lover's local lemma is just outside of reach. So we need to be a bit more clever with how we do the vertex selection. And the key is to go at it in rounds. So let me just give show a picture of how the algorithm works. So within each round, the point is that ideally we would like to control how many, let's say here, how many edges we have selected between Sij, Sik, and Sjk, between these 3 parts. But that's too much to ask. So instead, we just focus on how many edges there are that have 1 vertex here in Sij and the other 2 in the other 2 parts. And just let's say that we will be happy if this is roughly the number that we expected. What we have gained with this is the fact that now, whether the selection on Sij is good or not, is completely independent on whether the selection on Sik is good or not. So we have gained an some extra bit of independence. And then once we are satisfied with our choices in the first round, we go to the second round. And then we also look at the choices of vertices that have 1 vertex selected in the second round, 1 vertex selected in the first round, and another selected somewhere. And once again, the choices that we make here in the second round are independent. They are not independent with the choices that we made on the first round, but once we have fixed those, the choices on the second round are independent of each other. And eventually, in the end, the key is that we will only look at triples of at the edges which have 3 vertices which are selected in 3 different rounds. We will ignore all the triples of vertices that have 2 vertices selected on the same round, but fortunately, these will represent only a small proportion of the total number of triples of vertices. So long as the count of edges in the other between 3 different rounds is close to what we would expect, the global edge density is going to be close to what we would expect. So we are not out of the woods yet. There's still it's still not easy to make these independent choices. But I am going to leave it here because the time is going now. I can say a few words about how we do this selection, and in fact, I have an analogy for how this selection works, but I will leave that only if anyone asks about it. And I understand that this is the 9th talk in a row for most of you, so I understand if you are tired and you do not want to see it. So thank you.
So can you tell us how do you do this last step?
Okay. Okay. First of all, if there are any other questions, I would go with those first. But
I have a question.
Yes.
So your result implies that an optimal sequence of examples is given by a palette. Like if I have some fixed f, the uniform Turán density is given by taking some palette and taking the hypergraphs that generates. Do you think there's sort of a structural result that in fact the only way of getting a hypergraph that's uniformly dense and avoids f is via a palette, or is there some way of doing something that's more complicated but just happens to match the palette?
Okay, I know that there are so you will notice that I mentioned something this being the supremum of all the palettes and not the maximum. There are cases in which there's actually not this supremum is necessary.
I see.
But even in the cases in which a palette does satisfy it, I don't know whether it is the only construction.
Mm-hmm. Thanks.
Okay, any other question? Okay. So I want to say, so the way that I wanted to describe this selection, so I wanted to describe it as sort of selecting players for a tournament. So let's say that we want to organize some tournament between n players, and we want to play we want them to play games like two by two. Every pair of players are going to face off in one game. But the key here is that we are not going to make them all play the same game. We are going to choose some, like for every pair of, we can select a different game. So for example, these two are going to play like marbles, but we can choose a different game for each of them. And we want all of the players to feel that all the matches are fair. Not just their own matches, but also all the players that other players play. So let's say, for example, let's say that this player says looks at players 2 and 3 and says, "Oh, player 2 looks much stronger than player 3, so I do not want tug of war as the game." So, so then the question is, so what we are going to do is we are going to let each player veto 10% of the list. And then the question is this, so can we build such a tournament out of some players? Now, of course, if we have 10 players, this might not be be possible. So for example, it could be that for two specific players, A and B, each of the 10 players is vetoing exactly 10% of the list, and those 10, then we are not going to succeed. But let's say that actually we have many people interested in joining the tournament, and we just want to find M of them, which are compatible. Is this always going to be possible? And the point is that we want M to depend only on, the number of applicants to depend only on the number of players in the final tournament. So yes, this is possible, but here's the hard part. Selecting these games randomly is not going to be a guarantee to succeed. So we can see that for every triple of players, there's at least 34% chance that, okay, there's not going to be any mutual vetoes between the three if you select the games that they play randomly. But this is not going to guarantee that you can build a large clique. On the other hand, it's also not a Ramsey problem, because it may happen that there's no single game in your list that allows you to build a tournament out of them. If you could allow the number of applicants to depend on the number of games in your list, then yes, that would be possible. But if the list is allowed to grow to infinity, then Ramsey does not work. And instead, what you need to do is, like, essentially, and here's where it's important that we gain some independence. For every set of M players, essentially all the choices of games are independent. So if it is impossible to find such a tournament, it must be because there's a set of two players such that the veto list for the match between these two among all the players in your group is just the entire list. And so what you need to do is you're going to take all your players, you're going to take an ordering of them, you're going to mark, okay, so here my two bad players are on position 4 and position 9. And you're going to apply Ramsey's theorem to those bad positions. And then you are going to show that you are not going to be able to build a very large clique where all the impossibilities are precisely on the same players. So again, it's not a direct Ramsey problem. It is not going to be solved by probabilistically, at least not naively. You need a combination of the two. And it is important that we have gained this extra bit of independence of, okay, if you cannot build a game out of these players, it's a problematic pair. So here, essentially, the players are representing the indices of the hypergraph. The list of games is the list of vertices in your each of the, so yes, it's a set of vertices in your reduced graph. And then the veto correspondence is just when do you have an edge or not. Or actually, when do you have the right edge density in one selection or not. So that's, this is the important part that I wanted to say, is that it's not a purely a probabilistic proof, and it is not purely a Ramsey, and to gain an extra advantage with this independence.